Hi guys, today I'd like to share with you another paper. Its name is RefineGAN, universally generating waveform better than ground truth with highly accurate pitch and intensity responses. It's by Xu Shengyuan with his or her colleagues from Time Domain Inc. First of all, the authors mentioned that GAN methods would introduce uncertainties into the generation process and result in mismatch of the pitch and intensity, which cause the artifacts or fatal in terms of the singing voice synthesis. This is why they propose the RefineGAN. This is called a hi-fi neural vocoder. It's fast and it's robust, and it can also offer high accuracy in terms of the pitch and intensity. This is a full band audio generation. Okay, that means it can generate up to 44K. The contribution mentioned by this author is that they are able to eliminate defects proposed by the speakers and the recording procedures. But this is eye-opening for me. And they also can perform on totally unseen languages and totally unseen speaker as well. But this is also eye-opening for me. And yesterday I did have listened to their samples. I think their samples are amazing. I would say amazing. I think I haven't listened to. This is probably the best samples I've ever heard this year, and so this is a very good quality work. I highly recommend everybody who come up to here, give a listen to their samples here. Just search time domain RefineGAN. You should be able to get it. Okay, introduction part. They first talk about the conventional neural recorders. I think the main take-home message is that the quality reduced waveform delivered by those conventional vocoders are not very good. And also, they mentioned the vocal splitting tool, which is not good for handling high quality generation. And also, their application scenario, for instance, it's singing voice synthesis, so they need high quality. Okay. Therefore, they designed a approach called a pitch-guided approach. And this approach also alleviate the necessity of conversion from the time frequency domain to the time domain from the neural networks. I think I'm not a TTX expert, but I understand this. What they meant when they mentioned this sentence, it meant the vocoder's input are MFCC-like coefficients or coefficients from the frequency bands, okay? And then you have a sequence of those frequency coefficients. And then the vocoder task is to convert these sequence of coefficients into the time domain, the wave samples. So this process is super difficult and it creates lots of artifacts, something that's not natural. Okay, and the authors, they said, okay, they spare the task of this. Let's see what they do. Okay, and then they provide this method to level down the learning difficulty. And what is more interesting thing is that They mentioned that for training and validation data, they're recording in a studio, usually in a high fidelity recording scenario. But sometimes they are recording with the flaws and losses. And then they provided a way to refine those training data and validation data. So the random flaws or information losses are no longer presented in their training data. So this is interesting. Let's see what they do. What they mentioned. Related works. For TTS or singing voice synthesis, people do WaveNet, WaveRNN, autoregressive stuff, or non-autoregressive stuff like WaveGlow, WaveGrad, in terms of the vocoder designs. Okay, and WaveGAN is fast. I'm not a TTS expert, so I think I only read the paper of WaveNet, but didn't read those things. And they mentioned that MelGAN is the first GAN-based training for TTS vocoders. And they mentioned that high-fi GAN means they can do high fidelity voices. You can train the audios with up to higher sampling rates. Okay. I think this is very good background introduction. Very good. Then it goes to the description of their proposed work. I don't know why I cannot zoom in. Let's see. Control this. No, can't zoom in. Okay, I can zoom out. Okay. And they, the main network architecture in their proposal work is a UNet-like strategy. For those of you who are not familiar with UNet, please just go onto the Google Scholar and search UNet. It's a very popular paper, working very well. I think it originated from the medical imaging practice, and then speech people start to borrow that idea into speaker diarization and different stuff. Works very well, and it's interesting to see that UNet is also being applied to the TTS domain. I think they also, let's first look at there's the game changers. I think this is the game changer. Okay, it's called, check the section 3.2 speech template. I think this is a game changer. This is a new thing. They're different from other works. What do they mean by speech templates? Okay, let's see figure 3. Suppose we have a training waveform here. You can see on the left side part is speech. It's not noise, it's speech. Left part is speech, okay? And on the right part, it's also speech. And in this part, on the left and right part are voiced part. So speech, you can have voiced part like or right? And then in the middle, it's unvoiced part. So what's this unvoiced part? It's also speech, but think about S and you can see the waveform would be look like this. It's very up and down stuff, like here. So what they do is, for the voice part, they get the pitch value or the fundamental frequency at each time point, and they put a sample according to the speech envelope, okay, right here. But you say, what are the time span or time interval between the samples. So the interval at each time point is equivalent to the pitch period or the reciprocal of the fundamental frequency. I hope this is clear to you. But for those of you who are not familiar with what a pitch value or pitch period or fundamental frequency it is, just go ahead and Google yourself. And for the unvoiced part, I think they use randomized noise over here. But the amplitude or the envelope is attenuated based on the speech envelope here. So I just read the paper today. I'm still trying to comprehend what's the benefit of doing this. Probably once after I get that, I can record a extension of today's recording. But this is what they do. This is the template, okay? And then how the template is being used, okay? Then you have to see your loss function, right? So this is in section 3.61, envelope loss function. So right here. So the Y means the clean speech or the actual speech from your training set. And the Y means your estimated speech or TTS generated speech. I think this is L1 norm, but they use a pool function. Pool function you can, oh sorry, it's not pool function. It's a pooling layers output. Okay, you can regard it as, everyone knows what is max pooling. Okay. So this is what being used. But I'm still trying to comprehend what's the benefit of using the pitch period when generating the envelope function. So I'm still trying to comprehend that because I didn't see the what do you call that? Didn't see the term of the pitch period in the loss function. It's probably because once you change the pitch period, so the envelope can be different. So this is my question. I'm gonna read the paper later on. And also, they also mentioned that, okay, because I use a template developed based on the pitch value, so I need to estimate my pitch value. And they say the pitch value has to be estimated very accurately. But I didn't see in their experimental section any comparison of using a not very good pitch tracker versus their proposed pitch tracker. What if the pitch value cannot be estimated accurately? What the difference could be? They didn't have that comparison. What they did is they developed their own pitch estimator. Interestingly, I think they fused the methods of DO, harvest, and the ZCR, all the three methods together produce a final pitch curve. They have some math here. I think I decided to skip this because I'm the type of person who likes to see the comparison. If you're just saying, okay, this thing works the best, but I don't buy it if we don't have a comparative study. Okay. Pitch-based data augmentation. I think this is standard. People do this. I think this is standard. And also they do some resampling because you just shifted the pitch. The sampling rate should be changed. I think this is standard. And this is an example showing a lady's voice centered around 500 hertz. The high-pitched lady, I think. By doing the data augmentation, you can see the lady's voice got expanded to different regions. Well, I think this region is fairly low. I don't know whether anybody can have this low pitch, but they did some. They mentioned that they want the training to cover the rare cases or the unseen cases. Okay, and then they are saying that I think this might be new in their work because they didn't put a reference here. They're saying that traditional practice when calculating the male spectrogram-based loss when comparing the predicted signals male spectrogram and the ground truth male spectrogram, they used the same set of parameters when calculating the male spectrogram. I think for some reason they want to use a numbers of parameter sets to calculate the male spectrograms. So this is why they're not using a one single L1 norm. Instead, they're using a average of the L1 norms. Okay, but they still didn't compare the multi-param versus the single param. This is I think they need to do some extra work. The envelope loss function, I think I've covered this. Loudness-based data modification. I think this is standard. You have to attenuate the volume of the training data, so the training set could see all the volume cases. Okay. So they want to see the diversity of the data. The discriminator, okay, they use two discriminators. I think the first one, these are not new, I think. The first is proposed in the RefineGAN. The second one is proposed in the UVNet. And you can tell from the text, literally, meaning period means in the time domain, right? And the resolution means, I think it's probably like in the frequency domain, right? How does the loss function look like? So we have to jump to the equation here. So remember you have the multi-period discriminator, MPD, and multi-resolution discriminator, okay? So for the generator loss, because they're still doing everything in the GAN framework, they have to have a generator discriminator, okay? For the generator loss, okay, it's very natural. You have the envelope loss, we just mentioned that, and this part is the new part proposed in their work. This is the new part. The envelope or the template stuff it's a speech template. It's new. And the male spectrogram part, I think they mentioned that, and I think it's over here, equation 6. I don't think it's fairly new, but they use the multiple male scale based loss. Okay, and this part is the MPD and the MRD based loss. Okay, the generator. And for the discriminator, so in this time, the discriminator contains two parts, MPD and MRD. It doesn't have the mail or envelope again, nothing over there. So all you have is the MPD and MRD. I think this is very simple to understand. Very straightforward, very clean and nicely written to me. Understandable. Experiment. I think I will skip the parameters. I think it's interesting they choose the high, what do you call that? Hi-fi or high sampling rate. Probably this is why they can produce high quality synthesized speech or singing voice. I'm not an expert on this. For training data, they collect the training data from 12 different Chinese singers. Totally, there are 60 hours. Well, this is not much, I think. I think it's fairly not a difficult thing to collect the 60 hours of audio in a studio. And during the training, they didn't use any speaker ID information. Okay. Okay, talking about the results, I think after they generate that augmentation stuff, they generate 6,000 hours. Okay, and they do have a very good training GPUs. Okay, they conducted the MOS test by using real listeners. Okay, this is a good thing. Let's see their MOS testing result. I think this result is eye-opening, and it's I think I was surprised when I first saw this paper. This means their proposed method, the predicted speech or synthesized speech for both male and female, especially for the female, they can generate higher MOS score than the original speech. This is surprising to me. Does that mean the TTS synthesizer can generate better speech than human being or human singer? Probably. I think some singer on the live concert, they cannot sing as good as they in the studio because the tension and uncontrollable factors. But I think if I were the authors, I would also add another experiment, which is the A/B test. I think because the predicted ones are fairly close to the ground truth in terms of the MOS, I would do the A/B testing to see whether our listener can distinguish the predicted speech from the real speech, real singing voice. And the authors also shown the male predicted ones versus the ground truth. The female, I would say this is amazing. If you look at the spectrogram, it's almost perfect, very good. You can see it's almost identical to the ground truth. But frankly speaking, from the spectrogram, I cannot tell which one is better, the ground truth is better or predicted one is better. And also for the unseen speaker. So this means for those ones, this male speech, you have seen this male speech, okay? But this one, you haven't seen the speaker, you haven't seen the languages, okay? Then you want to do the prediction. I would say for this one, I can see it's a little bit worse than this one, I think. But it's still I think it's still very good in terms of the spectrogram. It's almost identical to me. And in the end, they also show in Chinese, French, Japanese, English, because the training data is from Chinese. Anyway, I think that the author also mentioned that what their future direction could be. Discuss the performance when constructing Mail spectrograms extracted from quality reducer recordings, and evaluate the quality boosts the vocoder brings to the reconstructed waveform. That's very useful because think about you got some training data which are not recorded in the studio. For instance, I just grabbed my cell phone and recorded in the classroom. It's not as good as studio, right? It has echo, has background noise. How would that work? I think this is a very good future direction. I would expect the author to come up with a new work on this. Finally, I want to see the authors did very good work. I highly recommend everybody to listen to their samples. Time domain RefineGAN on GitHub. So any questions? Questions from Wenjie. What do you mean by unseen languages? Does it mean synthesis another language sample? That's right. So their training data so I didn't read the details. But my guess is that their TTS, if you look at this, the network structure here, during the training you have this speech template and mail spectrogram as input, and you do this, and this is your target waveform, okay? And in the inference stage, my guess is that you also have this speech template. I think you have to either manually or automatically generate a speech template. It's not a big deal, okay? As long as you know where's the voice and unvoiced, you know what the pitch should be and what the word should be, you got the speech template and you put it into this. I think the speech template is language agnostic. You don't need to know the language. And the mail spectrogram, this is not this mail spectrogram is generated from another network. For example, Tacotron, okay, or the mail spectrogram. Oh, this has a typo here, huh? I need to tell the other. The mail spectrogram is an output of another neural network, which input is the text or some other control signals. For instance, you do the Japanese TTS. So the input are some Japanese characters, and then you have a control how long the duration of each word or each phoneme should be. You have all these controlling parameters, what the pitch should be for each word or for each phone. Okay, then you got this mail spectrogram. It's supposed you already got this mail spectrogram, I think. So this thing is not a TTS, it's the vocoder in the TTS, which converts the mail spectrogram into the waveform. So I guess this answers Wenjie's question. Okay. If no questions, let's stop here. And thank you people for coming. And everybody is welcome to present his own work or the latest archive paper he thought is interesting. Um, if you want, feel free to send a message to me on the Meetup. The Meetup is Speech and Language Technology Meetup group, and thank you, Wave Inc. for supporting this event. Thank you everybody for coming, and have a happy Friday, and thank you for coming. Goodbye.